When light's reflecting off of rain droplets, they're big enough to act as prisms, but it's reflecting off of small droplets. Something different happens. And if you have things which are small, the light scatters. What happens is this. It hits the boundary between like air and water or two different materials, and if they're small particles, it gets sent in lots of different directions. We say it scatters, okay? That's what happened last time when I had the laser beam and I had the chalk dust. Hits the chalk dust and it scatters, goes in all different directions. Everybody in the room could see it because of that. Smaller droplets do this. Droplets in clouds are small compared to rain droplets, but they're big compared to the wavelength of light. And so as a consequence, the light that's scattered from cloud droplets scatters all wavelengths of light equally. So the color of a cloud appears to be white. And it's because it's scattering all the colors of light essentially equally. And so they all come back. The color that you see is white. Clouds are, of course, made of water droplets, which are clear, and air, which is clear. And the only reason they appear to be white is because the light is sent in all kinds of different directions. And so it's all kind of like mixed up. It's a diffuse phenomenon. And it appears to be white because all the colors scatter essentially equally. Now, there's other things that work like this. This is my favorite. Your skin is made of transparent materials. You're mostly made of water, okay? And the part of you that's not water, like in your skin, is made of mostly collagen. And it turns out the bundles of collagen that's in your skin is mostly clear. It's clear. So you're made of clear stuff and water, which is clear. The only reason your skin does not appear to be transparent is because of two things. One, scattering. Two, pigment. The only pigment that you can have in your skin is melanin, okay? And melanin is brown, and so we can be shades of brown. That's the kind of like range of colors that humans can come in. But if you don't have melanin in your skin, and these are some albino babies, if you don't have any, they don't have any pigment in their skin, and they appear to be white, because then what's happening is the light is scattering. And there's a little bit of red blood in there too, so they look a little bit pink. But ultimately white. This color and this color, same thing. Same thing. And so your skin, if there's no pigments, is white for the same reason that clouds are white. It's ultimately due to scattering. But here's the amazing thing. The light scatters at the boundary between a water droplet and the air because of the differing index of refraction. If the indices of refraction are the same, you do not get the scattering. You do not get the reflection. I have a wonderful demonstration of that. This is a glass of Wesson oil. And there's a glass animal which is inside here. Check this out. And if I put it in the glass, it vanishes. And the reason is the index of refraction of Wesson oil is identical to Pyrex glass. Only like Wesson brand. I should get like a product placement for this. Okay? So it's only Wesson oil. And so the light hits the boundary between the glass and the Wesson oil, and it doesn't reflect, it doesn't refract. And so what you see is nothing. Here's the glass animal. There it is. And if I put it in, it's as if it's vanished. Here's the thing. You could do this. You could do this with your skin, because your skin is made up of two things that are clear. Suppose that you were to change the index of refraction of the water in your cells. Oh, yeah. If you index match things, you could make yourself transparent. And they're creatures that are transparent, and they do this by matching the index of refraction of the different materials that they're made up of. This is some glass fish here. And the glass fish are truly transparent. We used to have a tank of them in the Little Shop of Physics, and we put a polarizer film on the front and the back at like different angles. And it turns out when the light goes through, it changes the plane of polarization. And so they had these like cool rainbow colors. And it was a really kind of a neat thing. And it was remarkable. But it wasn't so good because like kids are like sticking their hands in the tank, and we could tell that we were headed for trouble here. The fish were not going to be happy at some point. So we stopped doing that. But totally clear, and you can see, look, you can see through them, and you can see the leaves behind them. Very, very cool. But you could do this. You could do this. Because all you need to do is you have to match the index of refraction of the collagen to the fluid in your skin. And if you add glycerol to your skin, you can do that. Here's a little test pattern that's put underneath the skin of a rat, which had injections of glycerol to match the index of refraction. And you can see the pattern through the skin. Initially like this, turns into looking like that. And so you could do this. In theory, you could have like skin cream that would like make your skin like transparent. If it ever became fashionable for people to be able to like see your blood vessels or something like that, you could make your skin transparent. Oh, love that. Now, turns out the things that scatter the light are big compared to the wavelength of light, but they're not that big compared to the wavelength of light. And as we'll see in a minute, scattering depends upon the wavelength. And it turns out the colors, your skin scatters the colors the same mostly, but when you go into the infrared, not so much. Infrared doesn't scatter so much because the wavelength's longer, and it's beyond a boundary where it scatters so much. So it turns out infrared actually goes through your skin. Your skin is transparent. Your skin is transparent. It's made up of things which scatter light. But infrared doesn't scatter so much. This is a little video clip that was taken in the Little Shop of Physics. This screen is part of a demonstration we have, which is called intravenous infrared, okay? And you can see this person's veins here, and that's because her skin is essentially transparent. And the infrared doesn't scatter as much. It goes right on through. And it's showing not her veins. It's showing the blood inside her veins. And we can see that because if you squeeze the blood out, they vanish. And when the blood comes back, so does the line. And this was a woman who was traveling with us. She's got a really strong effect here. Her name was Dana, but I started like calling her Dana, and this kind of like stuck. And for the rest of the trip, she was known as that. It was just because it was such a strong effect. Here's the thing, too. Infrared, since it penetrates the skin, you want deep heat, radiant heat lamp that gives off infrared? Oh, yeah. Goes in through your skin. Will actually warm up the blood inside your blood vessels. Is that cool? Oh, yeah. Now, let's talk about scattering from things which are even smaller. Things which are really small, like air molecules, scatter. And the scattering is much bigger for short wavelengths than for long wavelengths. There's a really strong variation with wavelength, okay? So as a consequence, when light scatters from the sky, the light that's scattered, you see mostly the short wavelengths, not the long wavelengths. And so the color that you see is blue. Cloud droplets, big. They scatter all colors. They appear white. Air molecules, small. They scatter mostly blue light. And so you see the sky is blue, clouds are white. Now I'll show you a demonstration of this as well. And we can see how this works. I've got this thing here. We call this the sunset egg. Big egg. And it's a glass egg, but it's got all kinds of imperfections in it that scatter light. And if I take a red light and shine it in, it looks distinctly reddish. And you can see the red light makes its way through. But if I take a blue light and shine it in, the blue light doesn't make it through. The blue light scatters out the back. So when you're looking at the light that comes to the egg, the blue light scatters and comes out the bottom. The red light goes out the top. So if I put in red light, what happens is this. It breaks into colors. The blue light comes out the bottom. The red light goes out the top. So if you're looking at where the light's coming from, it's reddish, yellowish. If you're looking opposite the light source, it's blue. So if you're looking at the sky opposite the sun, it's blue. If you look at the sun at sunset, it's red. Okay? And it's all because of scattering. It separates out the spectrum that way. And so that's why you have blue sky and red sunsets. It's because of this Rayleigh scattering. Someday a child will ask you, why is the sky blue? And you can say, okay, first off, we're going to have to talk about the concept of wavelength. Different colors, different wavelengths. Well, it's really frequency because it's photon energy. But let's skip that for a moment. And if you go into the whole thing and do like the fact that like the dependence is a 1 over lambda to the 4th, and so the difference between red light and blue light is about a factor of like 12 for the amount of scattering, do that. The child will look dazed and confused, but they'll thank you later, ultimately, okay? So go ahead and go through the whole explanation. Blue skies, red sunsets, ultimately scattering.